Okay, great. Welcome back. We have the second talk, the last talk before the panel. Bruno, Balthazar, take it away, please.
Hi. Yeah, first I'd like to thank the organizers for this wonderful conference and for the opportunity to speak here. So I'll be talking about this work that's going to appear with Amit Givon, David Kutasov, and Emil Martinek on ADS3 with no BTZ black holes. So let me start by giving some motivation of why this is interesting. Like we all know, ADS-CFT is hard in the sense that we want to have a weakly coupled string theory on ADS, but on the other side of the duality, this is a strongly coupled field theory. So apart from some protected quantities, it's hard to explore both sides of the duality at the same time. And another reason why it's hard is, at least in most cases, the ADS backgrounds involve RR fluxes, and we don't really have a good worldsheet description for these backgrounds. So today in this talk, I guess we're going to try to get around some of these issues. In particular, we're going to study a case which is a counterexample of this RR fluxes issue, which is ADS3 with a NS flux only. And then we're going to focus in the case where the ADS length is less than the string length. So it's a very stringy regime. And we're going to show that in some sense, it'll be clear that both sides of this duality are going to be under control. And the one analogy that's useful to keep in mind for those who are familiar is the example of non-critical strings and the matrix models, the usual C less than 1 matrix models. So let me just flash a picture here of where we're going. So the idea is that on the ADS3 side, we have ADS3 times some manifold M. And then we place P long strings in this background that are wrapping near the boundary of ADS3. And the dual of the system, we're going to see that is a two-dimensional CFT, which is of the form of a symmetric product orbifold, where the block of this symmetric product orbifold is of the form R phi cross M. So it's like the radial direction times M. And this will be a good description for large values of near the boundary of ADS3, provided that the ADS length is less than the string length. Okay, right. And the full CFT is going to involve some wall, for which I'll have some comments about in the end. But that's the general picture of where we're going. Okay, so let me start by first reviewing the construction of ADS3 cross S3 cross T4, which is not quite this example that we're going to be interested in, but we'll set most of the convention and also motivate our construction. And luckily for us, Emil already did a lot of the work. So the usual D1, D5 system has RR flux, but we can take the S dual to go to the NS1, NS5 system that only has NS flux and consider type 2 in this background. So we can consider, for example, R11 cross T4 cross R4 and place NS5 branes, N of them, on the R11 cross T4. And when you take the near horizon limit by sending the string coupling to 0, you arrive at the background that's given by R11 cross R5 times S3 cross T4, which is the usual CHS background. So the problem of this the CHS background is that the string coupling diverges because of this linear dilaton direction. So this is bad, right? So you can't really compute the string perturbation theory in this background breaks down. And one way to regulate this is to add P NS1 strings along the R1 cross S1. So here I've taken the R11 and compactified the spatial R1 to a circle, placed P and S1s wrapping the circle, and taking the limit where the radius goes to infinity. So that finally we arrive at the usual ADS3 cross S3 cross T4, where now the string coupling is essentially given by the number of NS1 strings. Okay, great. So this model admits a worldsheet description in terms of an SL2R WZW model at level K, where the ADS length is related to the level K in this way, written here. The worldsheet CFT has to have total central charge 15. And this condition essentially fixes that the level K is given by the number of NS5 branes, which is a positive integer, of course. So this is an ADS3, so it has a CFT2 description that lives on the boundary, and the space-time central charge of this CFT is 6K times P. So it's essentially as if you have each long string has a central charge of 6K. And the Sugra approximation, of course, is valid when our ADS is much greater than the string length. So that means that the number of NS5 branes has to be very large. Okay, so that's the worldsheet description. So let me mention some more facts about the SL2R WZW model, as was studied by Maldacena and Oguri in the 2000s. There are two types of strings that are that appear in this WZW model. One of them are the short strings, which are labeled by discrete representations, DJ. And this corresponds to strings that are bound to the center of ADS3. So they sort of just go, oscillating motions in the bulk. And the other type of strings are the long strings. And these correspond to strings that in the asymptotic past are wrapping the boundary of ADS3. Then they come in towards the center, and they scatter and go back out to the boundary in the asymptotic future. And for us, these are going to be the strings that are relevant because they're the ones that we're going to be able to capture in our space-time CFT, which are the ones that are near the boundary of ADS3. So let's focus on these guys. Right, so in a bit more detail, the SL2R spin J is written in this way in terms of a parameter P, which is like the radial momentum of the long string. And the parameter W corresponds to the number of times that the long string winds around the boundary of ADS3. So this is a good quantum number, provided the string is not, it is far from the center of ADS. The corresponding vertex operator is this phi, written here, and it has a given eigenvalue under the zero mode of the J3 current, given by the quantum number M. And so now you can form worldsheet operators, vertex operators, in ADS3 cross S3 cross T4 by combining phi with an operator in the S3 cross T4. Okay. And the space-time dimension of this operator just comes from the zero mode under the J3 current, and just by essentially from the value of M, which you can fix by the on-shell condition, you find the dimension of this operator of these long strings correspond to a continuous spectrum above a gap that's fixed by the level K. This is the gap. Okay. So that's the worldsheet description of this long strings in ADS3 cross S3 cross T4. But there's another description of these long strings, which is it corresponds to a CFT that's capturing the transverse oscillations of the long string. And this is called the Cybertheory theory. You can think of essentially as it being like a light cone gauge, in which you got rid of the directions in which the long string is wrapping, and you're just left with the direction that's transverse to it, so the R phi times the other direction, which is S3 cross T4. Indeed, you can combine an operator in the linear dilaton, this guy, together with the same operator that we had above in the S3 cross T4. And this linear dilaton related in some way to where the momentum S is related to the momentum P in the worldsheet in this way. And if this linear dilaton has a background charge, which is given by this equation, which just depends on K, you find that the dimension of this operator in the Cybertheory theory exactly matches the dimension above for the worldsheet. And furthermore, the central charge of the Cyberwitten theory also is the same as the central charge for a single long string. Because recall that the central charge of the spacetime CFT was 6 kp. So it's like you have p long strings, each with central charge 6k. Okay, so this seems to capture a lot of the dynamics of the long strings. Okay, so let's then look at the Cyberwitten theory in a bit more detail. The string coupling varies with the direction phi in this way, where QL, the background charge of the linear dilaton, is less than 0, because recall that k is greater than 1, is an integer that's greater than 1. And so what this means is that for large positive phi, the theory is strongly coupled, and for large negative phi, it's weakly coupled. And recall large positive phi is near the boundary of ADS3. So what this is saying is that when the long string gets close to the boundary, it's strongly interacting. So here, there are going to be non-perturbative effects. And the long strings can interact with each other and form things like BTZ black holes. Okay, so the dynamics gets very complicated. On the other hand, in the weak coupling region is where the long string description breaks down, because you can get near the center of ADS. The strings there can interact, can change winding. So essentially, the Cyberwitten theory is only valid here in some region, some finite region. Okay, so it's not really a good description in any of the asymptotics of phi. And so this is what is called a singular CFT. And the terminology comes from the fact that usually you think about turning on some RR vevs that introduce some wall in this region, in the strong coupling region, so that you don't quite access it. And when you turn off this RR backgrounds, RR fluxes, then you reach this singular CFT point. Okay. Okay, but one way to get around this that you can see from this description is that if I had taken k to be less than 1, then I'd have reversed the regions where the weak coupling and strong coupling in the phi direction are. So if k is less than 1, then the background charge takes the opposite value. So near the boundary of ADS3, then the strings are weakly interacting. And so in that regime, I don't have to worry about non-perturbative effects or BTZ black holes. And that's what we're going to try to do next. Yeah, so as I mentioned, we're interested in k less than 1. This reverses the slope of the linear dilaton. And to get the similar construction like what we had at the start, we're going to generalize the NS1, NS5 brane construction to now have curved NS5 branes that are going to be wrapping singular cycles. And this is based on the construction of Givon, Kutazov, and Pelch in '99. So how does this work? Okay, so we start with type 2 on R11 cross Calabi-Yau fourfold, where this Calabi-Yau fourfold takes the form of this equation in the 5-dimensional complex space. We take an NS5 that wraps the singular surface defined by this inside this Calabi-Yau fourfold, as well as the R11 directions. So we can proceed now in analogy with the ADS3 cross S3 cross T4 case, in which you take the near horizon limit. And essentially what you get is that the singular surface that the NS5 branes wrap, they have one direction that corresponds sort of a scaling direction that gives you the R phi cross S1, because you're scaling by a complex parameter. And once you get rid of these directions, you define you get a singular surface in a weighted projective space, which gives rise to a Landau-Ginzburg model, which is just the usual SU2N mod U1 with some ZNR before. But once again, you have this bad linear dilaton where the string coupling diverges. So you can add P NS1 strings to arrive at an ADS3 background, which takes this form, ADS3 cross S1 cross Landau-Ginzburg, and the string coupling is again finite. Okay, and now like Emil already alluded to, the condition that the total central charge is 15 fixes that the level K is given by n over n plus 1, which is less than 1. So we have achieved what we wanted to get a level below 1. And the ADS radius of curvature, which is root k times ls, is therefore less than the string length, and therefore there's a very stringy background. So we're going to need the full power of worldsheet CFT of the full background, but that's okay because it's an NS background, and we have the WZW model for SL2K. Once again, we have a CFT2 living at the boundary with central charge 6 kp. And so it's as if each long string has a central charge of 6K. Okay, so we can do the same steps that we did above for the ADS3 cross S3 cross T4 case and look at the dynamics of a long string, the worldsheet dynamics of this long string. So we have the same representations of SL2R, this continuous series, where P labels the momentum in the radial direction, the same worldsheet vertex operator for a singly wound long string. And you can form the worldsheet vertex operator now by combining an operator in ADS3 and an operator in S1 times Landau-Ginzburg. Just as in the case above, there's a Cyber-Witten theory, which comes from the transverse motion of this long string in the radial direction labeled by R phi, and in the other directions labeled by S1 times Landau-Ginzburg. So a full operator takes this form. It's an operator in the linear dilaton times S1 cross Landau-Ginzburg. And the background charge of the linear dilaton is the same as, it's given by the same expression in terms of K. But like I mentioned, K is less than 1, so now this is a positive thing. Okay, so now we can look at the Cyber-Witten theory again. The string coupling now grows towards the large negative phi region, so it's strongly coupled here and weakly coupled here at large phi. Recall that phi increases near the boundary of ADS3. So now what happens is that the long strings, they're not interacting once you approach the boundary of ADS3. So there you essentially just have a bunch of free strings and a Fock space description of them, of their dynamics. You might still worry about this region here in the strong coupling, and that's where the long string description breaks down, because the long strings can contract to the bulk and split and join. And from the point of view of the space-time CFT, I'll describe what this means. But yeah, I'll get to that in a second. The other thing that I wanted to mention is this point that Emil also already brought up, which is that essentially one interpretation of this is that the BTZ black holes, they become non-normalizable once you go to levels K less than 1. Okay, so this was argued for in this paper by Givon, Kutazov, Ravinovich, and Sever in 2005. So the high energy density of states is dominated by weakly interacting strings as opposed to BTZ black holes. Okay, right. Okay, great. So that essentially sets the stage for this symmetric product orbifold picture that we had, because the string interactions vanish near the boundary. So the long strings admit a description, which is essentially in terms of a Fock space. And we know that this is captured by a CFT2, which takes the form of a symmetric orbifold, where the block in the symmetric orbifold is the Cyber-Witten theory. And the parameter P is the number of long strings. So then you can have, depending on which, once you take the orbifold with SP, you introduce some twisted sectors, which are related to the cycles of the symmetry group of length P. And depending on the length of the cycle, this corresponds to a given long string wrapping the boundary of ADS3. So this is the picture that we have. We have P of these blocks, and essentially each one is labeling the dynamics of one long string. And here I omitted the Landau-Ginzburg directions. And of course, in order for this to be well defined, there should be some wall here, like already mentioned. I'll come back to this point in a second. But the full CFT, the picture you should have is that it's of these long strings that near the boundary are just described by a symmetric orbifold. And once you go towards the center of ADS, there's some wall that describes the reflection of these long strings and their interactions. Okay, yeah, and here's the usual story for the symmetric product orbifolds, that the long string that winds W times the boundary of ADS3 corresponds to a state in the ZW twisted sector of the symmetric product. In particular, if it winds only once, then it corresponds to some state in the block CFT2. Okay, great. So yeah, to understand better what we can do with this kind of asymptotic picture and what's going on with this wall, it's convenient to think about another example where we have something like this linear dilaton. And the toy model that we're going to think of is just a linear dilaton direction times a circle. So it's just a simple two-dimensional CFT. So again, you have a region of strong coupling and a region of weak coupling, depending on the value of phi. And of course, you want to cut off the strong coupling region so that you have a well-defined CFT. And there are different ways of doing it. So for example, you can add a deformation that it's a cigar deformation that essentially changes the topology of this cylinder and turns the system into a cigar, or the SL2 mod U1 model, like in the picture above, so that you don't ever reach the region of infinite string coupling. And another way of doing this is, for example, by adding a Liouville wall in the phi direction. So you still have the topology of the cylinder, but now the field phi can't quite probe the strong coupling region because of this exponential Liouville wall. Okay, so these are different walls for the same asymptotics in the weakly coupled region. Now we can ask, okay, what are the types of operators in each of these theories? So one type of operator are delta function normalizable. And this you can think of as, as if you're solving the Schrodinger equation in the weak coupling region. So the wall doesn't matter there, and you just have ingoing and outgoing waves. And the idea is that all that the wall does is that it provides a reflection coefficient that relates these two ingoing and outgoing waves. Okay. Another type of operator you can look at are non-normalizable operators, which essentially grow in the weak coupling region. So they're growing exponentially here. And you can think of these as, for example, analytically continuing the delta function normalizable in P. So for generic values of imaginary P, you're going to get two solutions, one that grows exponentially and one that decays exponentially. And the leading behavior comes from the exponentially growing one. And this gives a non-normalizable operator. Finally, you also have normalizable operators, which give rise to normalizable states. But these guys are very sensitive to the wall. So we can think of these as, for example, the ones that are related to poles of the reflection coefficient. So, it depends on the reflection from the wall. And for example, in the two walls that we used as examples above, the SL2 mod U1 has normalizable states, which corresponds to strings that are near the cap of the cigar, but the Liouville does not have any normalizable states. So in other words, in this picture of the symmetric product that we had, we can't say anything about normalizable states at this point from the space-time point of view, but we can still talk about what we call the long strings, which are the delta function normalizable and non-normalizable guys. So what we actually do is, we use the exact ADS3 worldsheet to derive what is the dictionary between ADS3 and space-time CFT2 for these long strings. So for the delta function normalizable and non-normalizable. Since, like I mentioned, these do not depend on the wall. So the precise mappings are kind of technical, so I'm not going to get into that. But the general idea is that essentially the way the mapping works is that the wave functions on the two sides of each description match each other. as you'd expect.
Would you say again what the space-time theory is?
The space-time theory, let me show you this picture here. So it's essentially, well, for this case that we're considering, it's R phi cross S1 cross Landau-Ginzburg to the power P mod SP. And then you have to introduce some wall to make this CFT well-defined, which is what I was going to get to now. But in the region of large phi, that's what it looks like.
Okay, thank you.
Yeah. Okay, so, right, so you need to add some wall that's going to shield the strong coupling region and make the CFT well-defined. Otherwise, we can talk about anything like correlation functions and these kinds of things, because these quantities are sensitive to the wall. So in order to motivate the calculation, let's consider a simpler example, which is type 0 on ADS3 cross S3. This is related to the construction of NS1 and S5 that I gave above by a squashing of the S1 and a different GSO projection, but it's not important. One difference is that, of course, the type 0 is going to have a closed string tachyon, but we don't have to worry about it for this purpose. So yeah, we want to analyze the worldsheet spectrum of the theory. So in the W equals 0 sector, we have a closed string tachyon plus some RR vertex operators. And we also have worldsheet operators for the holomorphic currents of the space-time CFT2, which in the case of ADS3 cross S3 corresponds to Virasoro and SU2. And this was known already in this early works of Givon and Kutazov and Cyberg in '98. Then we can move on to the winding one, because these guys are the ones that should appear in the block of the symmetric product orbifold. So we're going to have normalizable operators, which are sensitive to the wall. And we're going to have what we call the long strings, which are the ones that are not sensitive to the wall, which are the delta function normalizable and the non-normalizable operators. And in particular, what we find in this winding sector is that we find more holomorphic currents of R phi cross S3. By identifying their quantum numbers, we find the holomorphic current partial phi. We find the bosonic SU2 holomorphic currents, as well as holomorphic currents associated to the 4 free fermions of R phi cross S3, which form an SO4 at level 1. So in other words, the W equals 1 sector precisely matches the spectrum of R phi cross S3, at least of the delta function and normalizable guys. And another interesting thing is that this holomorphic currents, we don't quite expect them to be there in the full theory. So just like in the example of Liouville, for example, we have R phi, and then we have once we add the wall to modify this to Liouville, the current holomorphic current partial phi is no longer holomorphic. So this is no longer equal to 0, and it's not equal to 0 because of the wall. So it depends on the wall. Or in other words, it vanishes exponentially in the large phi region. So in other words, we can try to use this holomorphic currents and explore their lack of holomorphicity to derive what the wall operator is. And we find that indeed this wall operator, by this calculation, this worldsheet calculation, it gives an operator that vanishes at large phi. Okay, some preliminary results suggest that we have to turn on an operator in the block. So inside each R phi cross S1 cross Landau-Ginzburg, as well as an operator in the Z2 twisted sector. Okay, so one way to think about it is that you have this asymptotic region here. And then once you go near the bulk, there's some interactions that essentially, some deformation that essentially allows the long strings to interact with each other. Of course, the Z2 twisted interaction is what you'd expect, because you want an interaction that does not conserve winding. So it allows the long strings to join and split. And it's exactly what a Z2 twisted deformation would do for you. Okay, guess I finished a bit early, but just to point on some future directions. So like I mentioned, the space-time wall is one of the things that we're exploring right now. Some work in progress. And then once we have that, it'd be nice to understand how to map worldsheet scattering amplitudes to correlation functions in the space-time theory. Because like I mentioned, these guys, the space-time theory correlation functions depend on the wall, even for the delta function normalizable and the non-normalizable operators. It'd also be nice to understand what is the role of the W=0 sector. So there you have some normalizable states, and therefore they're sensitive to the wall, and how they fit into this space-time CFT picture. So it could be that one has to use something like FZZ duality to map them to winding 1 and higher, and then they still kind of fit into the symmetric orbifold picture, but it's more speculative. And then we also like to understand what are the role of the conserved currents that appear in the winding 0. In the sense that the currents that appeared in the winding 1 and higher, they don't seem to be conserved, but the ones that appear in the winding 0 seem to be conserved. And finally, I mean, like I mentioned at the start, this is kind of a generalization of this non-critical strings and matrix models that we had in lower dimensions. And so this seems to be a generalization to ADS3 and CFT2. It'd be nice to know if we can do this to even higher dimensions and find the general, some more general constructions and dualities. But yeah, I don't have much to say about this, but that's all I had to say. Thanks.
All right, thanks very much. I'm sure everybody's very happy that you were able to wrap up within the time. Especially Nick, he likes his breaks. Yeah, so any questions for Bruno?
I have a question. So
yep.
So when k is less than 1, you have some kind of winding condensate that grows at infinity, right? On the other hand, you were describing the background as having, let's say, p strings. And to me, there seems to be a slight tension between these two statements. In particular, you kind of assume that when you go to the ADS3 picture, you have a certain flux that you can vary and you can tune, right? That was where the number p was coming from. Mm-hmm. And my question is, well, that is somehow, well, I know an argument based on gravity that shows this. Can you show that this is also the case in the in this k less than 1 case? In other words, the quantization condition for the electric H3 flux.
I thought the quantization for the level k, you mean?
No, not for k, but for p. I think you called it p, the number of
strings.
Right.
On the ADS3 side, right, there's nothing that really tells you that p has to be quantized, because it's only related to the string coupling in this construction.
Yes, but you were assuming that this is a controllable quantity that you can vary, right?
Yeah, I was assuming that I can tune the string coupling. Yeah.
Right,
but I think you can just start with the worldsheet and CFT of ADS3 cross S1 cross Landau-Ginzburg with some string coupling, and then you never quite have to talk about P from that point of view.
Okay, well, let me make a comment which might not be directly related, but there might be some connection. Mm-hmm. So if you think about the cigar conformal field theory, it has a zero mode, which is the coupling constant at the tip, right? Mm-hmm. But precisely at the same value of k that makes the winding mode non-normalizable, also makes the string coupling non-normalizable. Because it's just the same mode, it's just a different manifestation of the same mode. Mm-hmm. So that's why I was worried about this point. Mm-hmm. maybe it's irrelevant, but it sounds somewhat relevant.
Yeah. Yeah, I think this is related to this fact that the SL to our invariant vacuum is no longer normalizable, right? In this k less than 1.
Right. So the question, perhaps another way of asking the question is whether this interferes in any way with the quantization of the electric edge reflux. I mean, this. Anyway. The reason that I was asking is because for k bigger than 1, you can think of this background as having these p strings. So the total winding is p somehow. That's localized near the tip. But for k less than 1, there is some condensate of winding mode that goes all the way to infinity. And if you were to calculate the amount of winding, I think you would get some infinity. That's why I was asking.
Yeah, I'm not sure.
Okay, well, I don't want to.
You should maybe say we are still a little bit confused about exactly what the wall means and what its nature is. But one thing's for sure, that our current candidate for the wall is a normalizable operator in the space-time theory. So,
yeah,
there is some tension between your observation that the worldsheet theory, it looks like the ADS3 wall for k less than 1 is not normalizable, but the wall we were suggesting for space-time is a normalizable deformation.
Okay. Yeah, I think my question was mainly purely about the infinity region. I mean, I agree you will have this space-time wall that you're discussing, but I think my question was more about the interpretation of the whole theory at infinity. In other words, in what sense do we really have finite p?
Yeah, I think from the worldsheet, you don't really see that finite p. It's probably be something non-perturbative that we don't have access to. So yeah, maybe I should have said that in the space-time CFT, we're really thinking of taking p to infinity there.
Well, p is asymptotically large in order to have weak string coupling.
Right.
So.
Yeah. Yeah, in other words, p is 1 over gs squared. So it's non-perturbative in the string coupling.
Okay, thank you.
Are there any more questions before we take a somewhat longer break? Okay. In that case, let's thank Bruno again.